Hi, we will start with the study of relational query languages. And our first example of a relational query language will be relational algebra. We are working with the relational database systems. And the idea one of the ideas of creating a database is that eventually we want to manipulate the data. We want to retrieve some specific data. For example, let's suppose that we designed a database for a university, and then we put all the information in a set of tables. We got table of students, courses, uh, takes, and departments, and all other tables that maybe we decided to create. But then we got a request, what we call a query, and then they want the names of the students who are CSCI majors that took all courses offered by the history department in the summer of 2012, whose GPA is greater than 3.2, that were born in Kenosha, and that also took a course from the geography department, for example. Then we need something that will help us to retrieve that information easily. So that's why we have the query languages. So relational models provide us with, because of the mathematical base that we're using set theory, they give us a lot of options with these query languages. And we shouldn't confuse a query language with a programming language. The idea of the query language is we want to, our main emphasis is will be like a tool that will help us to retrieve data, any piece of data that we store in the database. So like here there are odd things that we are not able to do with a query language. We will experience that with examples. Now, there are two mathematical approaches, again, because our model is based on set theory. We can use either relational algebra or relational calculus. In this course, we just will study relational algebra. Now, what we do, like in the example that I gave you before about a possible query, is we know the schemas, what is it that we got in the relations. For example, in the students, we have the schema, maybe the name of the table is a student, then we got a student identification, a student name, age, address, GPA, major, department, and maybe the social security of the advisor and so on. So that's what we call the schema. And then when we provide when we ask the query, what we do is we're manipulating some relations, and then at the end we also get another relation as the result. But we also want to see the data, the instance that is in that data. Now, something else that is important, since we're talking about that a relation is a tuple, and the definition of a tuple is like the position of the data there. It is important. So, for example, a tuple can be maybe the open parenthesis 1, 4, 6. So that is a sequence of elements in a tuple that can be an element of a set for a table. So it's not the same if I change the order of those numbers that I just say. It has to be in the sequence. So the first number maybe represents the identification, the second maybe represents the name, the third represents something else. Now, these are examples of some tables that we will use to illustrate the use of relational algebra. Let's suppose that we've got three tables of three relations, R1, S1, and S2. So those are instances. So R1 comes from the table reserves, in which the schema comes from the SID, the sailor identification, the boat identification, and the day in which they make a reservation. These are in your textbook. And then sailor is the sailor identification, the sailor name, the rating of that sailor, and the age. So here we got three possible instances, and we're gonna go back and forth to this slide to work with examples. Now, this is the main thing that we will study for this topic. We will work with some of the basic operations, which is selection, projection, cross product or Cartesian product, the set different and the union. Now there are others that are not needed, but also that help a lot, which is the intersection. The join is going to be one that is really helpful in the division. And then what we will do is we will combine those operators over the relations to be able to manipulate. And this is the idea of the query language. With these will be like my tools. Using these tools, I should be able to extract any piece of information that is being requested from me. And remember, we're getting as an input a set of relations, and then my answer is still a set of relations. So that's what it says. The algebra is closed. Closed is because I'm not getting out of the set that I get. I mean, I'm getting my input is sets, and then my manipulated and the answer are also sets, which in this case are relations. This is the first operator, projection. So projection is we're going to identify that with the symbol pi, and then, for example, if we do pi over S name and rating, what it means is on table S2. Let's go back to table S2. So this is table S2, and then we want to project over, what is it, S name and rating. So S name and rating is like we just go over column S name and rating, and we're getting these elements from here. So these are 1, 2, 3, 4 elements that we're supposed to get 4 rows, and that's what we're getting from there. Now, for example, if we go and project over H on S2, let's go and see that column. S2, you see that the column H has 35, 55.5, 35, and 35. So there are 3 sailors that are 35 years old, but when we do the projection over there, we get 35 once, and we don't get it 35 3 times. Now here we're asking why. Well, the idea is that this is the idea is that we're manipulating a set, and then in sets we're not supposed to have duplicates. So we cannot have 35 3 times. That's not allowed in sets. Now, for example, when we implement this in SQL, and we said, okay, do the projection over this column, we will get duplicates, because the way that they implemented, they just have a pointer to that column and display all the elements from there, and they don't make the distinctions that we're repeating the elements from there. The second operator is selection, which we use the symbol sigma. So with that sigma, the idea is that we select some specific rows. If we go back to the previous one, when we project, we're projecting over columns. So I want to see these columns. I want to see, for example, the column H. Give me that information there. Now here I want to see a specific rows or specific tuples. So for example, the one that says sigma rating greater than 8 on S2. It says from table S2, show me the rows which the attribute rating is greater than 8. So let's go back to the original table. So for example, here on S2, greater than 8, the rating will be the 9, the 5, and the 10. And that's what they should show here. I'm sorry, the 9, greater than 8 will be the 9 and the 10, right? I'm sorry. So here is the answer is the 9 and the 10, and that's what we're getting here as the answer. Now, something that will make the query even more interesting is the combining those. So for example, here, if we read this query, it says, give me the name and the rating of those sailors whose rating is greater than 8. And then this is solving a specific query, the one that we gathered. Now, union, intersection, and set difference. So, for example, here, we got the S1 union S2. Now, to be able to do the union, in this case, this is what is called a binary operator. Why binary? Because we're going to need 2 relations. In the other ones, look, we were all using the sigma over 1 relation, so this we call that a unary operator because we only needed 1, and the same with pi. So here we need 2. Now, to be able to do 2, it cannot be any 2. It has to be some that we call union compatible. So let's go back to the instances. So for example, R1 and S1 are not union compatible. Why? Because first R1 has 3 columns and S1 has 4. So I cannot union them because they have to have the same number of columns, and then they need to be compatible too. Like for example, SI and SI is okay, but BID and SName in the position, then it's not the same. I mean, it's not comparable. Like for example, maybe this is a number, maybe this is a string. However, S1 and S2, they are union compatible. So I can do the union, I can do the intersection, I can do the set difference. So that's something that we need to check. When we want to union, intersect, or apply the set difference, they need to be compatible. Okay, so on here, when I do S1 union with S2, it's the same idea that you got from set theory on doing the union. So let's see here if we got any duplicates. So I think the SID 31 is here, and the 58 is there. So remember that when we do the union in sets, we don't get duplicates. So it will be these three elements for whatever is not on there, which is 20 and 28 and 44, right? So there will be 5 in total. So those are the 5 that we have here. And this is the example of the set difference and the intersection. So S1 intersected with S2 will means sailors that are in S1 and in S2. And then the S1 minus S2 will be sailors that are in S1 but are not in S2. And then you can go back and check that information there. Now the cross product is a very expensive operator, and it's also called the Cartesian product. So for example, let me see, in here, so in this example we are doing the Cartesian product of S1 and R1. So you see here we got each of the elements of S1, and we pair each of the elements of S1 with each of the elements of S2. So let's go and see how many elements we got in S1 and how many elements we got in R1. So in S1 we got 3 elements, and in R1 we got 2 elements. So for example, these 22, with the SID 22 and 58, 22 should be paired with each one of these, and 58 should be paired with each one of them. So it will be 2 elements times 3. We should have 6 elements as the answer. So here are my 6 elements, in which each one of the elements from one table is paired with the other element of the other table. Now here we're illustrating a conflict in the resulting, because we got 2 columns that had the same name. So we got 2 ways of solving this conflict. Either we rename the row symbol that looks like a P, is a symbol to rename, and then we says rename number 1 is the first column of table C, and rename that as SID1, and the 5th column rename it in this resulting table as SID2. Or we can just put the names of let me see, the first one is the table S, I think it's S1. So the 22101 is that one. So for example, one of the SID is going to come from table S1, and the other is coming from R1. So we can do S1.SID and then R1.SID, and that will also solve the conflict. Now finally, for this tutorial, we will study the join operators. So for the join operators, will be like implementing a Cartesian product but with some conditions. So for example, it says, okay, it's like doing the Cartesian product between R and S, but with the condition that only in which the identification of one is less than the identification of the other. So you see the SID here is 22 and here is 58. So only those are the ones that we want to do. So when we got this type of join, this is also called the theta join, which we specify, which is equivalent to a Cartesian product with a sigma. You see that that's what we say previously, that the join is not really needed, because this can be substituted by using a Cartesian product and a sigma. But this is really helpful, and we want to use joins a lot. Now we got 2 type of joins. So when we implement joins in which we do equal conditions, like for example here, the in which the For example, SID in both cases is the same, then we call it equal join. And then natural join is when the names are the same. So for example, the in these examples R1 and S1, if we do the join where SID is the same as SID, that will be a natural join. Why? Because it's an equal, and the spelling of the attribute here and the spelling of the attribute here is the same. If the spelling were not different, we just call that an equal join. If we're doing any other type of condition, that's the one that we call theta join. We will work on the next tutorials on some of the we will practice on solving actual queries with these operators. Thank you.